Right, for the OS, this week's lecture we covered synchronization between processes after recapping a little bit the different types of semaphores and which one to use whenever we want to make sure that we have mutual exclusion, for instance, and which one to use if we're trying to count the number of available resources or keep track of them, whether there's a number of them or it's an individual resource that we're keeping track of. And the purpose of today's lecture is to have a case study that happens between concurrent processes and try to analyze it, fiddle a little bit with it, and then finally we're gonna talk a little bit about messaging between processes, so how processes could talk to each other. Right, so concurrent processing, and in the case study I'm talking to you about today is the producer-consumer problem, consumer, and this is one most common problems that we have when it comes to concurrent processing. And by concurrent processing, I mean processing trying to execute at the same time, fighting over to be able to execute at the same time. So even if we have which is the premise of the whole course, a single core CPU, well, we still have concurrent processes because of the impression of parallelism that we talked about, and we're going to cover in more details in the upcoming lectures. Right. So let's see an example here. In the face-to-face lecture, we tried to imagine the scenario, and the best way to illustrate it is using an analogy. So we have a pizza machine here. We're gonna call it the producer, and then it will deliver pizzas each and every time. We're gonna put some coins in it, well, some money in it, fair enough, and we can see that the pizzas are aligned on a table, and we're gonna call for some reason the table a buffer, and then at the other end, if we have the producer, we should have the consumer. In this case is our beloved Joey from Friends. Right, so the idea here is try to analyze the problems or the constraints regarding that particular model here. Where's my laser pointer? Yeah, so we can see that first off, go ahead and try and pause the video and think about the different constraints. And once you resume that, you're gonna find you should have thought about well, I can only produce so many pizzas that fits on the table, right? Because if I overdo it, well, they won't fit, so I'll be dropping them. That's one. So there should be some kind of synchronization here. And second, and most importantly, well, Joey shouldn't be able to consume something that is not there. So if there are no pizzas on the table, well, Joey shouldn't be trying to consume anything at all. Right? There's a critical resource in my system here. What is it? So the critical resource here is, by definition, something that is shared. So a shared resource, as we've seen in last week's lecture, it's the shared resource is a critical one, and there's always a critical section dealing with a critical resource. So the shared resource in this case is none but the buffer that we have here. So it's shared between the process that is the consumer and the process that is the producer. Fair enough? So we need to regulate the access to that particular shared resource, which is the critical one. Right? Inside of pizzas, this could be generalized to englobe any kind of data. And one last thing here is that Joey, even though I'm sure, not doubting his skills, he would be able to eat everything at once, but I mean, he cannot get and consume but one pizza at a time. Fair enough? So let's see. If the buffer is full, I should not add any elements because it will overflow, and I don't want that to happen. And if the buffer is empty, well, the consumer shouldn't be able to remove any elements from it because there are none. But for now, for the sake of simplicity, well, we're going to consider that the buffer is infinite, and the producer can go ahead and just put things in the buffer all the way to infinity and beyond. Alright, so yeah, it's a shared resource. I want to try and protect the system using binary semaphores, and this is a decision. Use anything else, but let's go for a binary semaphore. I should have some kind of, if I'm talking thread-wise, I mean everything that is true for processes, as I said earlier in earlier lectures, is also true about threads in a way or another, because threads could be seen as mini processes. Alright, so let's see two different threads, one for the producer and one for the consumer, and then we're gonna have the main function. So the producer, indefinitely, he's gonna produce, or she, so they're gonna produce something and append it, so put it in the buffer. And once we put something in the buffer, well, we're gonna increment n. So n most probably would be the number of elements in the buffer. Fair enough. And most probably I'm gonna initialize it with the value 0, because my buffer would be empty at the very beginning. Empty. Right. So if I have a producer, I should have the consumer, and we can get inspired by that in order to produce the consumer. Well, the consumer would look like something like the producer, but instead of producing, it will be, I mean it's because it's a thread, it will be consuming, and then it will be taking something out of the buffer, and when it takes something out of the buffer, well, it should decrement n as well, right? So it goes something like that. Indefinitely, I'm gonna take each and every time I take something from out of the buffer, I'm gonna decrement the number of elements on the buffer, and then I'm gonna consume it. And lastly, here we're seeing the main function with n being initialized, and you can see that it's a global variable. It doesn't really matter for now. And there's a special function here, a call, that kicks off both the producer and the consumer, and we can decorticate a little bit here. Begin, yeah, means start, so we're starting both of them, and par, maybe it should be parallel begin or something like that. So basically we are kicking off both of them at the same time. Alright, so let's see. I wanna protect the buffer using a semaphore, so a binary semaphore, and the two options that I have when it comes to a semaphore is either to increment it and decrement it. So I decrement it whenever I'm taking the key of it in a way or another, and then I'm incrementing it whenever I'm gonna give it back. So in order to protect the access to a particular part of that code, which is the critical section, I'm gonna use the semaphore. So I'm gonna surround it with two different functions here, right? I'm creating a semaphore with the initial value of 1, so it's a binary 1, it's 1 or 0. Creating it with the value of 1 means that it's created with the possibility of someone being able to take it. So it's created with a key, it's created open, unlocked. There goes the producer. This is the code that we had earlier, and then I'm gonna surround the part that is critical for the buffer by a sem weight, and at the very beginning the producer is attempting to take the semaphore. It's available, so it will be able to do so. So it appends, increment, and then give it back. Comes the consumer now. We're waiting for the semaphore. It's available. I'm gonna take whatever the producer has produced, and then I'm gonna decrement the buffer, right? And then I'm going to consume. So you can notice everything related that is shared is being protected here in a way or another. And I'm still having those. So awesome. There we go. Okay, so take a second or two and think about the problem here. The problem here is whether the consumer is the first entity, the first thread to go first. So this means that the consumer at the very beginning, with n being equal to 0, it will attempt to take the semaphore which is available. It will take it. It will decrement n from 0 to negative. Oops, I'm not allowed to do that. So whoop, there's a problem. Let's try and fix it. Go ahead, pause the video, take as much time as you want, and then resume it in order to see the solution. This would be a good exercise for you to prepare yourself for the exam, because at the exam you won't be able to, to read the solution or to get the solution. You'll have to come up with it yourself. Right, so let's see. So apparently the main problem here was the fact that the consumer could go first. So I'm gonna try and synchronize in a way or another. I'm gonna try and tamper with the fact that it can go first and make sure that it doesn't go first. So I'm gonna use another semaphore. Remember, a semaphore at the end of the day is a signaling mechanism in a way or another. So I'm creating a semaphore called delay here with the initial value of 0. So this time this semaphore is created locked. Hence, this is solving all my problems. So if I kickstart both of them and the consumer goes first for some reason, it's going to wait on the semaphore, and the semaphore is blocked. It's locked. So the consumer will get blocked. Hence, it won't be able to continue. The other one, this one will go from running state to the blocked state, and then the CPU is free to get the producer, and hence the producer will get into the CPU, does its thing, and then once I made sure that I added an element in my system, since element number 1 added to the system, I can go ahead and try and make the consumer start, even if the producer keep on executing for some for some way, or for some other reason. This means that I've already signaled the delay semaphore to be able to be taken by the consumer. However, I would have more elements here, but let's stick to the fact that I only created one element, and then I signaled the thingy, sent back my semaphore, my original semaphore, and I gave the CPU back to the consumer. So this time the consumer is having a value of 1 because I just signaled my delay semaphore. So I will be able to enter here, do whatever I like, take the element from the buffer, hand back the original semaphore, consume it, and then, well, if I only had one element, so I need to get blocked again. If I had more elements, well, I can go back to here, do the thingy, as long as I have elements. If I'm sticking to the fact that I only have one element, this means that after consuming the element, n will be 0, and then I will be stuck back to, blocked, waiting for the producer to produce at least one more element. Isn't that beautiful? This is a solution. Whoops, there's another problem with that. Well, so take your time to analyze it, and then go ahead and trace it with me in the next slide. So let's do that. I'm trying to trace. This is the code. These are the variables that I'm interested in, notably n here. And then you have the consumer and the producer. Let's see. Let's make the producer go first, because anyways the consumer will be blocked if it attempts to go first. So let's do that. So the producer went first, attempted to take the semaphore S, was available, it got it, it incremented n, it signaled delay, now delay is available, and then it signaled back S, so S is available again. Now comes the consumer's turn. The consumer can get the semaphore, which is 1 now, so decremented it, trying to take S, which is 1 here, it took it, and then it's trying to decrement n is equal to 1, so n will be equal to 0. Then once it's done, it's going to signal this original semaphore S, so S is back to 1. Alright, so the thing that happened here, instead of continuing, for some reason I was kicked out of the CPU. So some preemption happened, and the producer is going into the CPU again. And this could happen because outside the critical section anymore, so I don't have any constraints about that. So what would happen here? Let's see. So we're back to the producer, to the while true. So I produce, I'm waiting for the semaphore which is available, so I'm good, I can take it. I'm gonna increment n, good for me, and then I'm gonna check if n is equal to 1, so I'm gonna increment the delay semaphore here, and then I'm signaling back as a classical. Now I'm back for some reason to the consumer. So remember, two processes are concurrent, are fighting over the CPU. So one of them went through, and then the other wants to continue what it started. And remember, we stopped at consuming here. So should we go back to the beginning of the while, or should we continue? So if you remember your lecture about the PCB, and we need to save the return address and everything, this means that we need to resume from wherever we stopped last time. So the process stopped here, or the thread, doesn't really matter. It stopped here, so it should continue from here. So let's see what happened here. If n equal to 0, well, let's check this out. N is equal to 1. Nope. So I'm not going to wait on the delay, so I will continue from here. It's an infinite loop. So some wait is trying to take the semaphore s. S is available, so I'll be able to take it. Good for me. I'll take the element, decrement n here, so n went from 1 to 0. And then I'm gonna signal s, which is done here, so we're good. Fair enough. And then I'm gonna check if n is equal to 0. So yeah, this time I continue it instead of going there. For some reason, that one did not ask for the CPU for now. And we're gonna see more about how processes fight over the CPU later in the very next lecture, I believe. Right, so here now I'm continuing here, so I'm checking if n is equal to 0. It is the case. I'm gonna go ahead and wait. However, you have noticed that delay is equal to 1 here. Whoops, that's bad. That's bad because I can go back to here, take the semaphore, which is the original one s, which is equal to 1, so I am able to take it. I'm gonna take something and decrement n, and we got to a negative value. So -1 here means that it's a big problem. It's an issue, and it shouldn't happen this way. So yeah, how to solve this problem now? So we try to amend a problem with a solution, and the solution caused another problem. So how to deal with it now? Right. So here it goes. This is a solution, not just the solution. The solution which is mine, but it is a solution. You can create your own solution as well, as long as it's valid. So the whole point here is to make sure that I'm testing the original value of n. So the idea here is, you can notice that I decrement the current value of n, and I put the value in m, and here I'm not testing the new current value of n, rather I'm testing the one that I use inside my critical section. Get it? So in a way or another, I made sure that this test is made inside my critical section. You can go ahead and trace it and verify that it's correct. And as a good exercise, you can try and come up with another solution that it should be valid as well. Alright, so we talked about semaphores. Now I want to talk about monitors. And a monitor will be an entity that is used as semaphores, and it will help in regulating the access to resources. Now I want you to see the monitor as an object from an object-oriented point of view. Let me get my pen. So in semaphores, the problems, and we've seen an example of a problem, is we need to surround the critical sections with this proper semaphores and make sure that they're synchronous, etc., etc. And this could, because we are humans and we are the one who are coding, so we're prone to errors. What if a better service is provided by the kernel? What if we dispose of monitors? In this case, instead of surrounding ourselves, using functions that deal with the semaphore, well, all we have to do is invoke an element, an object, right, and use it without tackling the code itself, without adding extra instructions, to protect the critical section. Let me explain myself. You can see the semaphore as a room in which you would be able to use your resources. Fair enough? And each process that needs to use one of the resources, let's see, this is the printer, this is the scanner, this is one I/O module, doesn't really matter. So each process wants to use any of those, needs to get into the room, use it, and once it's done with it, it will leave. Fair enough? Now, from a practical point of view, how does it, because the process is not a human being, it can't just, walk in the room. So in order to enter the monitor, all we have to do, remember your Java courses, if you want to use an object, all you have to do is invoke the object dot one of its methods, right? So it's the exact same thing here. So all I have to do is call one of its functions. So the function that will allow me to use the printer, for instance. So if there's no other process in the monitor when I'm trying to get into it, I'll be able to get into it and then use the printer. And once I'm done with the printer, I can go out. Fair enough? If others are trying to get to the monitor while I'm in the monitor, there will be some kind of waiting list. We good? And this solves so many problems. One of them is the deadlock, because it's only one process at a time that can get any of the resources. Right? So it's equivalent to semaphores, but it's way easier to control. Right? Let me see here. So here we're seeing the actual better schematic of it, better than my drawing for sure. Laser pointer. So here you can see the processes that want to use the monitor, and they want to use the monitor by using one of its procedures. So procedure 1 could deal with the printer, procedure K could deal with the scanner, or something like that. So if P1 wants to use the scanner, it will directly go ahead and use procedure K, and no other process can enter so no other process can get the printer where the P1 is using the scanner, for instance, because only one process is allowed in the monitor at a time. And here you can see that once we're done, we can exit it. What would those be? So imagine you're using the printer and suddenly you're out of papers. So the condition that will allow you to use the printer is not there anymore. So instead of leaving, because you cannot leave if you're not done, you're gonna get, in a way or another, blocked. So you're gonna go to another, let's call it a balcony now. This is the room and this is the balcony, where you're gonna go ahead and wait for someone to load some papers, for instance. And these are what we call conditions. So we do synchronize by using condition variables. So if a process is using something and the condition that it was true at the beginning is not true anymore, so I have no papers as I'm using the printer analogy, for instance, I'm gonna get blocked within the monitor here. I'm gonna wait for it to be true again. So if I'm at the balcony, so the room is available for another process to use something else. something else, because if it attempts to use the procedure which condition made me get blocked, well, I'm gonna get blocked again. All right. When the condition is true again, and provided that there's no other processes in the room anymore, in the monitor anymore, so I can get back. Fair enough. That's it. At the very end of the slides, I've given you an example of codes implementing a solution for the producer-consumer problem using monitors, so you can check it out on your own. Right, last thing I talked about and you should be aware of is that processes can talk to each other. So we've seen in a very early, maybe the first face-to-face lecture, when we talked about processes, that processes could share a common memory space, partially. So there's a segment in memory where it's shared by two processes or more, and this is to make communication easier. Well, if they have no shared memory, well, there should be another mechanism for processes to talk to each other. So someone can send a letter. So a process can send an information, a message to another process. And the message should contain, well, in order to know how to route it, well, the destination process, because there might be more than two processes. So P1 needs to say that it's meant to go to process number 2 and not process number Z, for instance. Right, and the content of the message itself. Now let's think a little bit about, that's a cute animation, is it? Let's think a little bit about synchronization first. So let's see, if I have something to send and try to map it to human beings. So basically, someone wants a calculator before entering the exam. So basically, the process that is expecting the calculator, for instance, or the student card or whatever, something that you need prior to getting the exam, will not move forward before the thing that they need is there. And this guy, who's supposed to give the calculator or the student card or whatever to P2, for instance, well, should do nothing else but to make sure that this guy got it. Alright, so yeah, so it feels like they're giving themselves some kind of appointment, right? And this means that they're gonna be blocked until the message has been delivered. So the sender and the receiver, both of them, they'll be blocked, and this is what we call the rendezvous. And in English, we use the French word of it, so it's a rendezvous, but with an English accent. Alright, that's one possibility. What if this guy wants to send to multiple things, or what if that guy wants to receive from multiple people? Yeah, so you can imagine the different approaches as well. So we could have a non-blocking send, so I can send it and then continue. However, this one won't be able to move until the message is received, or it could be a non-blocking end and a non-blocking receive, and no one will care about, I won't be waiting for the message to arrive. I'll just continue whatever I have to do. And of course, this depends on the implementation of the kernel. Alright, so we thought about P1 sending something to P2, so it needs to specify to talk directly to P2. Fair enough? So the message will go directly to P2. It will be handed over directly to P2. However, first off, we're gonna call this direct addressing, right? So we're directly giving, P1 is giving the information in P2. Now, if there's direct addressing, naturally there should be some other fold. What would that be? So it could be indirect addressing, and in order to implement indirect addressing, we're gonna use mailboxes. So instead of handing over yourself the letter to the other human being, all you have to do is go ahead and put it's in mailbox, and the human being will go and get it from its mailbox. Fair enough? So let's imagine different schemas here. So we can have a single sender putting something in the mailbox for a single receiver, or single sender putting a message in the mailbox for multiple receivers. It could be same message or different messages, doesn't really matter. Or multiple senders trying to send to multiple receivers, And finally, what would be the last figure? Well, would be something like that, but inversed. So it would be multiple senders sending to a single receiver. And this special case, this is exactly what you have in networking, for instance. When you need to connect to a computer, to a server, for instance, or you're going to use a particular port, and multiple people can, multiple processes can connect to that particular process using that port number. Alright, so in this case, we call the mailbox a port. Right. Last thing that I needed to reflect on, and again, this is one typical question that I might ask in the exams, is well, which one? What is there? Critical resource here somewhere? Yeah, of course there's the mailbox. It seems that I need to make sure that I'm done writing before the receiver will get it, for instance. See, so this throws us back to our producer and consumer problem. Fair enough. And even it's more obvious here because we are multiple senders, so basically we need to regulate the access to the mailbox in order to make sure that everything is done correctly. Right? Alright, so that's it, and next lecture will be about the most important resource of them all when it comes to computer hardware, which is you should know it by now, the CPU, and we're gonna talk about scheduling of the CPU. Alright, so have a nice one and hope to see you soon. And by the way, this is the code that I talked to you about, so you can check it out in the PDF.